We have some more time. Let us do a topic called dipoles.
Okay.
Dipole is a combination of one positive charge and a negative charge placed very close together. And this distance here, this one, we call this twice a, so that the half point is exactly a distance apart from both of them.
Okay.
For a dipole, there are two things that are important. One is the axial point and one is the azimuthal point. What are these things? Axial point is anything that lies along this axis of this dipole.
Okay.
This point is an axial point. And you could also take a perpendicular bisector of this dipole. Any point on this perpendicular bisector is an azimuthal point. So it's important to know what the electric field due to a dipole is. Why? You might ask why? Why the special combination of charges? Why do I need to know? It's because in most ionic solids, say sodium chloride, potassium chloride, the ions actually become small dipoles. And if you were to understand the physics of these solids, you have to think in terms of dipoles.
Okay.
The electric field in those solids are like dipole fields. So
Okay.
it helps to know what these are, what the field at an axial point is, what the field at an azimuthal point is. So let's look at the axial point. Let's say it's at a distance of r, this point. What's the field? Electric field, we'll use the superposition principle. Total electric field must be the sum of electric field due to the positive charge plus the electric field due to the negative charge.
Yeah.
And the charges are, say, plus q and minus q. So the field due to the positive charge would be q by 4 pi epsilon naught r squared. But here the distance is r plus a. This extra distance is a. So from the positive charge, this is r plus a whole squared. The negative charge, however, would produce a negative electric field. So minus q by 4 pi epsilon naught. Now the distance is a bit closer, so it's r minus a whole square.
Okay.
And now you take everything common and you do some algebra. Pi r square minus a square whole square. This is the a plus b minus b formula I used.
Yeah.
And top here you've got r minus a whole square minus r plus a whole square. R square minus 2ar plus a square
Where
minus
is r square
2ar
to
minus.
ar?
So things cancel off. R square
Where a square?
by minus a square. So what
So
remains is
it's minus 4 ar.
minus 4 a r q by 4 pi epsilon naught r square minus a square whole square. Now remember I said that the distance between the dipoles is the charges is very small.
Yeah.
We like to think that the distance is so small. Say you've got a sodium chloride atom. This is very small. It's a few Armstrongs. Very small compared to this small r here. So that we actually say that r square minus a square, this is very much equal to r square.
Okay.
Alright. So that approximately this turns out to be a r cube by 4 pi epsilon naught r to the fourth. And there's a cancellation. So you get your final 4aq by 4 pi
Pi
epsilon naught.
epsilon naught r cube.
So for a usual charge, you saw that the force fell off as 1 by r square. But now you see for a dipole, the force falls off faster at 1 by r cube.
Okay.
So this effect is called a shielding effect, because there are
Okay.
two charges, both of them shield the influence of each other. Now, conventionally, we call this minus 4aq factor. You take minus 2aq, not minus, plus 2aq. You call this the dipole moment P. Okay, it's customary to write this as that, so that your expression becomes 2p by 4 pi epsilon naught r cube. And this p here is actually given a vector property. So the p is from the negative 1 to the positive 1. So negative, positive. This is your direction of p vector. And so you can actually put the vector here, and this will give you your electric field as a vector. Fine?
Yes, sir.
Okay. Let's stop the demo class here.
Okay. Thank you, sir.
Okay, good.